All right, here we go on our next video. This is a follow-up from last time where we did the derivatives of sine and cosine, and we went through the process of how that came together. If you're interested in finding out where the rest of these trig functions derivatives comes from, there's actually a fairly simple derivation of most of these, just kind of using substitution of what's going on. Quotient rule, for instance, with tangent. But for now, all I'm going to throw at you is you have in your workbook, you have all 6 of these listed here. These are your derivatives of your primary and reciprocal trig functions, and we will use these quite often. And so you'll need to know these. When you take calculus next year, they may or may not be provided for you, so you'll have to remember what these are. But through some use of this and just getting used to using these, they will all become pretty commonplace to you. It doesn't take too long for you to get your head around these. First one, sine, of course, we saw the other day. Sine, derivative of that is cos. Derivative of cosine is sine, but our new ones that we're going to use is the derivative of tangent. It says it's secant squared. The derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant tangent, and then the derivative of cotangent is negative cosecant squared. So here's a list of all 6 of these. What we should start with is notice that, just in notation, that tan of x squared, for size, yeah, that'll work just fine. So tan of x squared does not mean tan squared x. So the one on the right here is usually what we will end up using. This whole idea of tan squared means tan x times tan x. This is usually what we are going to mean by this. Occasionally you will see where you're squaring your angle, but not very often. Most often we're just dealing with the square of tangent, and we write it as tan squared x like this. Becomes quite a regular thing that we will have to use. So determining y prime for the following function, if we have 1/2 tan 4x, so of course we're going to have to use chain rule with this. And so chain rule, derivative of the outside function, inside stays the same. So the outside function is going to be 1/2. We take the derivative of tangent and it ends up being secant squared. The inside stays the same, it's 4x. And now we take the derivative of the inner function, which is 4. This all simplifies to 2 secant squared. There's our final answer. Our next one, y is equal to secant squared square root x. If this helps you, especially in the beginning, we might want to write this as secant of square root x all squared, just to give ourselves a reminder that that secant squared means secant times secant, secant root x times secant root x. And if that's the case, now we're going to take our derivative. That 2 comes down front. The outer function is squaring. The inner function is secant root x. So we have 2 secant root x. Now we're going to take the derivative of the inner function. That inner function is secant root x. And as we look in our table, derivative of secant is secant times tangent. So we're creating a product with this. The inside remains the same when we do this chain. So this remains to be root x. That's your inner function of this. So in our first step, this was the outer function, was the squaring, and the inner function was secant root x. In our next step, once we've done that, the inner function, that secant root x, now when we take the derivative of it, the derivative of that is secant root x times tan root x. That's your inner function, and that's now what we have to differentiate. And so we have that, all of that stuff times 1/2 x to the negative half. There's a lot in here that we're going to do some cleanup with. In our next step. We have 2 times secant root x times secant root x again times tan root x times 1/2 x to the negative half. That coefficient of 2 and of half, they divide away. We end up with secant squared root x, because there's 2 factors of that. There's tan root x upstairs, and then our last part is this is all over root x prime, and we're done. Whew, lots going on. Cosine of tangent x squared. So we have chain rule of a chain rule. So again, we have this outer function, which is cos. The inner function of that is tan x squared. And that, of course, has an outer and inner part as well. So we take our derivative of cos. Our derivative of cos is negative sine. Inner stays the same. The inner part stays the same. And that inner part is tan x squared. It is the angle that's being squared here. That doesn't mean tan x times tan x. That means tan of x squared. So we take our derivative of this inner part being tan x squared. We've got an outer function to that, which is tan, and an inner to that, which is x squared. So we end up with secant. So we are multiplying this by secant squared. The inner stays the same as x squared. And now all of that times 2x. We should probably rewrite this a little bit. And we have negative 2x. It's going to be written up front. We have sine of tan x squared. That is a separate factor from this secant squared of x. Here it is. So we really need to be kind of clear about what's going on with chain rule. By this point, this gets so deep, we're often going to have chains within chains. And so if you aren't solid on looking for what your inner and what your outer functions are, and keep in mind, so I'm taking my derivative of the outer function, inside stays the same, times the derivative of the inner function, you're gonna get yourself in trouble pretty quick. So you have to be for sure clear about what's going on with chain rule. Number 4, we have negative cotan of x minus 1 squared. That squared written there, it is squaring x minus 1. That's all the angle. Whether or not we see this with, this is cotangent of all of that, that's implied in this question. So we have the negative of cotangent. Looking up above, our derivative of cotangent is negative cosecant squared, and so therefore y prime will equal positive cosecant squared. Inside stays the same, times your derivative of that inner part, which is just 2 bracket x minus 1 to the 1, times the derivative of the inner part, which is just 1. Tidying that all up. We would normally write any binomial factors out in front of our trig factors. So 2x minus 1 cosecant squared, x minus 1 squared. And that's it. Sine 3x over tan 3x. We could go ahead and do this with quotient rule and chain rule, and it's going to look a little nasty. Or we can clean it up a little bit, recognizing that tangent is just sine over cos. Important to that is the fact that the argument in here, this the angle that's written in here, is the same. If this was sine 3x over tan 2x or something like this, we would not be able to do this. And so to clean this up is really a good idea with this. So this is still just going to be y, and this is sine 3x over cos 3x, then this of course ends up being cosine 3x. Much easier to take a derivative of. The derivative of cos is negative sine. Outside stays the same. And then times the derivative of the inside, so I'm just going to change this to negative 3. Be sneaky with this. All right. Almost done here in this short little video. Determine the equation of the tangent line to the curve. Y is equal to sine x tan of x over 2. We are going to do that when x is pi thirds. So our first step is find our first derivative, because we will need the slope. We've got product rule going on here. Derivative of sine x is cos x. Tan x over 2 stays the same. Product rule, so we're adding this. Sine x stays the same. And the derivative of tan of x over 2 ends up being secant squared x over 2. Side stays the same. And then times the derivative of x over 2, which is a half. All right, so if we want y prime at pi thirds, to find out what the slope actually is there, we're going to take cos pi thirds, tan pi 6, right? Pi thirds divided by 2, sine pi thirds, times secant squared pi 6 times a half. I'm going to write that half over here out in front of my sign, I suppose. So we need to think about on our unit circle what's going on here. We've got pi 6 for some of these angles. We've got pi thirds for some of these angles. If I've got cosine of pi thirds is the short side. So this is just 1/2. It's the short side of your 30, 60, 90 triangle. Tangent of pi thirds is your y over your x. So that ends up being, tangent of pi 6. This didn't look like a 6 in there, but it should be. This should be tangent of pi 6. So tangent here is 1 over root 3 plus a half times sine of pi thirds. Sine of pi thirds is root 3 halves. And then secant squared. So secant is your reciprocal of cos. Cosine at pi 6 is going to be root 3 halves, but it's secant. So I'm going to take the reciprocal. So there's your reciprocal of the root 3 halves that you would have for cos. Don't forget that we need to square it because it's secant squared of that. Lots of little things to remember. I'm not going to try to simplify this denominator until I know what I'm dealing with in this second part. So 1 over 2 root 3 plus, what do we have here? 4 root 3 upstairs, all over 2 times root 3 squared is 12. Ends up being equal to 1 over 2 root 3 plus root 3, 3. Let's get a common denominator here. Let's multiply this up and down by 2 root 3. This one up and down by 3. And at the end, after all that is said, we've got 3 over 6 root 3. It's 2 times root 3 times root 3, 6. Ends up being 9 over 6 root 3. Ends up being 3 over 2 root 3. And if we're wanting to rationalize that denominator, that's 3 root 3 over 6 root 3 over 2. Through simplifying, there's different ways of getting there, but hopefully we all got to that as our slope. Remember that that is now a slope. We are wanting what? We want to find our equation of our tangent line when x is pi over 3. When x is pi over 3, y at pi over 3 ends up being equal to sine pi thirds. Tan of pi thirds over 2, which is tan pi 6, which is root 3 halves, divided by tan pi 6, which is 1 over root 3. All of that together ends up being 1/2. So therefore, point that we are using is pi thirds on 1/2. And let's just finish this off. Therefore, in slope point form, we've got y minus 1/2 is equal to root 3 halves x minus pi. So lots going on in there, just lots of algebraic manipulation and numerical stuff going on. But this is pretty deep in interpreting trig derivatives and using chain rule to find what's going on here. So lots going on in this question. Thanks so much, and we will see you next time.